Hey guys, this is GKCS. In this video, we'll talk about 30 white papers which are worth reading if you're a software engineer. I've gone through about 100. I've ranked them, scored them, and the top 30 are what we'll discuss in this video. So let's get started. Number 30 is scalability at what cost? COST is in caps. That's an acronym. The basic idea here is when we're talking about scaling a platform, scaling a service, we think about horizontal scaling, which is adding more servers. So whenever a request comes in, you can load balance it to the right server. The hope is that overall your system is going to react faster. Latency will go down. But this paper challenges that supposition. It talks about mainly graph algorithms which tend to perform much better in a single node than a distributed environment. Many of the assumptions that you have around distributed systems are broken here. It's definitely worth a read. It's a very easy paper to read also. It's not too dense as compared to the rest of the papers coming up in the lineup. Good paper to start with, number 30. Number 29 is detection of silent data corruption. This is a paper from Google. It talks about basically anomaly detection. If you have hardware errors or if you have errors which you want to detect very quickly in software, then this is a very interesting paper to read. In general, as a software engineer, all these papers are good, so you can go through it. I would give it a score of roughly 4 out of 5 because it's quite useful, quite good, but there is that hardware element which may not be very relevant to software engineers. Good to know though. Number 28 is profit, which is from Facebook. It talks about forecasting at scale. Facebook has a lot of data metrics that keeps coming in, and you need to be able to accurately forecast what should have been the right metric, because if you want to detect an anomaly, you need to see the difference between what should have been and what actually is. So observed versus what was predicted. Now, Facebook has this white paper where they talk about millions of metrics which are flowing into their system, and then they have to in real time detect anomalies. Worth reading. Again, I would give it a score of roughly 4 out of 5 because it's a pretty long paper. And it's got some things around statistics which are not core to software engineering. Still worth a read. Number 27 is Napa. This reminds me of a Dragon Ball Z character. I'm sure he didn't work at Google, unlike the engineers who wrote this paper. It talks about data analytics. It talks about a lot of the product metrics which are at Google are very useful when you're trying to find patterns. So Napa is a data warehousing analytics solution by Google. It was featured in VLDB, which is a very respectable conference. So definitely worth a read. I would give it a 4 out of 5 because it's extremely geared towards data engineering, but definitely it's amazing, so you can read it as a software engineer also. Number 26 is Cubrick. This paper is from Facebook. It talks about an in-memory analytics processing system when you are having distributed OLAP databases. OLAP is a particular way in which you store data in a database. If you have a lot of data, then maybe you don't want to store all of the data. You want to aggregate it, and then you want to perform analytics on top of it. That's what this paper discusses. It's from Meta, again featured in VLDB. Superb depth here. Little more towards data engineering sometimes. I'll again give it a score of 4 out of 5. I'll give it a rank of 26 out of 30, but 26 out of 30 amongst the 100 plus papers I've read is a really good rank. Definitely worth a read. Number 25 is near real-time server monitoring and root cause analysis. It's a really long paper name. You can probably get most of the idea of the paper just from the name. Root cause analysis, monitoring. So if there are problems in servers, then Facebook, who's written this paper, wants to detect that quickly. We talked about Profit earlier, which is a forecasting system. This is identifying, detecting errors, and also trying to guess what the root cause is. So one common technique of finding root causes for any problem is to ask many questions, the whys, the 5 whys. So if a server crashed, you ask, why did it crash? And then you say there was a memory overload. So why was there a memory overload? Because someone wrote code which was adding to a list infinitely. Why were there infinite additions? Because I didn't do rate limiting. And so in this way, you really get to the absolute root cause. It has some drawbacks also, this approach, but we'll not get to it. For now, let's talk about the number 25 paper, monitoring and root cause analysis. I'll give it a 4 out of 5 maybe, because it talks again about techniques which are not used every day as a software engineer. This paper is definitely worth a read. Number 24 is Presto, SQL on everything. As the name suggests, they want to run SQL on various forms of data stores. Okay, so if you have a graph data store, if you have a data warehouse, if you have any kind of data file store, then ideally you learn just one language and you're able to query data all around the world. Now, that's a dream, but for Facebook, it's almost a reality in the sense that they have multiple data stores, and what they do is they have connectors on top of these data stores which can be used to fire SQL queries on them. Presto is the language, you can say, or the connecting thing which makes this possible. It's worth a read. As a software engineer, it's very useful. As a data engineer, it's amazing. I would probably put this paper as a data storage or data analytics kind of thing. Worth a read. Number 23 is Foundation DB. This is a paper from Apple. engineering. It's an open source database. From what I remember, it's perfectly consistent database if you want it to. Allows transactions, and it is a NoSQL database. Transactions plus NoSQL has this new cool term called NewSQL, because earlier people used to think NoSQL doesn't have transactions. Now they have both come together. Apple has this paper which is quite interesting. What's the best part about this paper is the way they tested the system, making sure that their transactions work is quite novel, and they have videos on that. Read the paper. If you are super interested, go and watch the videos. It's nice engineering. Number 22 is F1 Lightning. This is a paper from Google, and it reminds me of Formula 1 cars going at tremendous speeds. They have also named it Lightning, so super fast. But the fact is that this is more of a hybrid database that they have tried to build. One is on transaction processing systems, so real-time production systems, and analytics also on top of it. It seems counterintuitive. Normally what happens in large-scale distributed systems is you have one type of database which is optimized for real-time production workloads, high consistency, transaction support, and there is another type of database which is basically rebuilt using this production data from time to time, which is optimized for analytical workloads. There are patterns also for this. There's something called CQRS, Command Query Responsibility Segregation. So you have commands here and you have queries on this read optimized database. Let's not get into that. If you take both of them together, what do you get? You get a hybrid. And what's the hybrid called for Google? F1 Lightning. Worth a read. Interesting concepts. Of course, nothing is perfect in the world, so there are some trade-offs that they have made here. Do check them out. Number 21 is from LinkedIn. That's the only LinkedIn paper that I see in this entire 30 paper list, and the paper talks about finding connection distance efficiently in LinkedIn. If I am connected to a person and you are connected to the same person and we are not connected to each other, what's the connection distance between you and me? It would be 2. So that would be 1 connection plus 1 more. But what if you want to find a connection distance of 2? In this case, you need to find all the people near you, and then we need to draw that circle even larger for the second degree connection, and then we need to find matches. It's a well-known, difficult problem to solve. LinkedIn hasn't optimized on the algorithm here, but it has optimized on the software engineering part, which is caching, finding out which connections should lie in which box. So you can run the algorithm efficiently in a single box rather than having cross communication across boxes. Amazing paper. It also links to many other amazing graph algorithm papers. Definitely worth a read. I would give it like maybe a 5 of 5 or 4 of 5. The only reason I'll dock a little bit of point over here is because it doesn't go into as much depth as I would like it to, but it's an easy paper to read. Number 20 is TensorFlow. This is an extremely popular paper, cited thousands of times, written by Google. It's featured in Usenix, so you know that the quality of the paper is pretty good. It's taken over a large part of machine learning systems. Definitely worth a read. Number 19 is The Monolith Strikes Back. This is an independent paper, although I found it in the Google archives. The idea here is that you don't always need microservices to scale your system. You can do so with monoliths also, and monoliths have certain benefits. They are easier to code. There's lesser complexity when it comes to deployment. If you remember the first paper we talked about, number 30, which was Scalability at What Cost, this is its sibling in software engineering. That would be in terms of DevOps. This would be in terms of software engineering. Don't get too excited about having thousands of nodes running graph algorithms. Here it's don't get too excited about thousands of nodes running your production services. Microservices are not always the solution. Monoliths work really well. That's the basic idea, but worth a read because they give it in a better language than I can. And I would say it's like a 5 on 5 or 4.5 out of 5 because very relevant, very useful, little less formal than I would like it to be, little less talking about numbers than I would like it to be, but an opinion. Number 18 is HALP, which is Content Delivery Network Optimization by YouTube. As you can expect, the paper is from Google, from the YouTube team. It talks about how they optimize their caching on the content delivery networks. When you're trying to fetch a YouTube video, you sometimes hit an ISP who's connected with Google. Google goes to the ISP, gives them a box called YouTube Red. You can think of this as a hard disk, which has a bunch of YouTube videos which are evergreen. It's like YouTube's cache in the ISP. The benefit of this is that you don't need to hit their servers every time. Most of the content is just placed in the CDN. If you want the hit rate to be high, you want your algorithm for eviction to be efficient for a cache. Google found that LRU, LFU, all of these algorithms exist, but HALP performs slightly better. It's a great way to introduce yourself to machine learning. Worth a read. For a software engineer, I would say that it's maybe 4.8, 4.9 out of 5. Give it a shot. From now on, every paper that I talk about is excellent. It's like 5 on 5. And number 17 is Monarch. Google Monarch is a time series in-memory database from Google. The basic idea here is that you have petabytes worth of metrics data at Google, and you want to be able to analyze that data very quickly. So you want to keep it in memory. The problem though is that you also want to detect anomalies. In case things go wrong, Monarch has to respond. Even if Spanner is out, even if Google's file store is out, you still need to be able to answer queries. Because if their engineers are debugging Spanner, then they don't want a system which is dependent on Spanner. That's an interesting way to think. How do you make a system so reliable or so independent that it doesn't need a database? Google talks about it in Monarch. Many optimizations talked about in this paper when it comes to time series. And it's a novel kind of thing for a software engineer. I would give it a 5 on 5. Definitely worth a read, although it's not very easy to read it. You need to probably go through it once or twice or thrice to get the general gist. I would suggest taking notes separately in a notebook or on a notepad, because that helps you visualize what these guys are doing. Number 16 is Dapper. Dapper is a tracing system at Google. So if you have a request which comes in and you need to trace which services this request hit and how much time they took and what was the response like. Normally what happens is you have these logs and you have a central area where different services post their logs. And now if you use a request ID, then you can search amongst all the logs together. So they all come forward sorted by timestamp. Dapper is a better system, I would say, or a system which performs this at scale. It's a system written by Google. Very interesting, used for anomaly detection and other things similar to request tracing. Worth a read. Number 15 is GorillaDB. This is one of my favorite papers actually. It's a highly optimized time series in memory database created by Facebook. It's now Meta. The basic idea was that you don't need all the data in the world to be persisted. You just need the last 26 hours data to find anomalies which have to be reported immediately. Facebook actually wrote a paper which talks about how it gets terabytes of data in their system and they are able to detect anomalies in real time. Number 14 is Zanzibar. This is an authentication system written by Google. It's one of my favorite papers because it has so many practical optimizations which it talks about. It talks about request collapsing. It talks about hedging requests. I've actually taken a live class about Zanzibar, GorillaDB, and these favorite papers of mine. It's at Interview Ready. I would recommend reading it though, because as a software engineer, often you're looking for some kind of optimization which is slipping through your fingers. You have some ideas, but it's not clicking. Zanzibar though works at a scale which is so large that they try to hit every single optimization that they can. So it's a good listing of optimizations that you can use when it comes to request processing. Number 13 is Memcache at Facebook. This is talking about an advanced caching system by Meta, earlier Facebook. What I really like about it again is that it talks about a caching system which they have used from almost startup phase to a mature company phase. That means they moved from a small engineering team which is just trying to survive, creating a social network which is scaling quickly, to a completely scaled, highly optimized social network cache. There are systems which have been written on top of Memcache at Facebook. So definitely worth a read. The optimizations are amazing. It's an old paper. I think it's written in 2013, and yet it talks about some of the amazing algorithms that you can use in your own cache. It's inspired many other papers. Uber, for example, uses a lot of ideas from Memcache. Twitter used Memcache. They used to call it Memcache. I would say it's a base, it's a foundation for many of the caching algorithms which are now visible in the world. Number 12 is SIEVE is simpler than LRU. It's a bit of a weird name. LRU is a cache eviction algorithm. SIEVE is actually an acronym here. Okay, it's an eviction algorithm. It's a very simple eviction algorithm, almost as simple as, let's say, LRU. When you are out of space in your cache, you have to choose an element to evict. And the benefit of SIEVE is that you don't need to jump around with your pointer. You can just go straight ahead, mark elements which have been visited already as visited, and you push it forward in your queue. It's like a priority queue in that way. If it hasn't been visited, then you evict it. So it's got some principles from LRU and LFU. Okay, the paper will give you more details. What I really like about it is that despite all of the years, decades of cache optimization, researchers have not given up and have discovered simple optimizations which tend to outperform really complex machine learning techniques also. So the paper is, as you can expect, it's an independent paper. It's a research paper from a university. It's a very new one. Definitely worth a read. Number 11 is also a caching paper. This is the last caching paper that we are talking about, but it's an analysis of hundreds of in-memory caches at Twitter. I really like this because it's eye-opening to some extent. Usually when we are thinking of caching, we are thinking about read-heavy systems. When we are talking about Memcache or when we are talking about Redis, we are thinking about a specific way in which caches are used. But in a very large-scale distributed system, you have various varied requirements. This analysis talks about how cache performance depends on the expiry, object size, and write rate even more than eviction policy. The previous paper was on SIEVE and eviction policy, which is awesome, but this will bring you more in touch with the practical aspect of things. Okay, when it comes to actual access patterns for caches, you have to consider a lot of things, not just the eviction policy. If you're an engineer, 5 on 5, surely. Number 10 is, I think, the only paper from Amazon in this entire list, and it's excellent. It's called Firecracker. It talks about virtualization. You can think of containers, micro VMs, all of those principles are touched upon in this paper. What I really like about it though is that when you think of serverless, when you think of Lambda in AWS, like you want to run your code without assigning a server to it, how does that work for Amazon? How do they do that in real time? What are some of the practical things they can do? Do they cache some of your container properties, or are they doing something else? Worth a read. Now I'll tell you that out of the 9 papers remaining, there's just 2 which are non-Google papers. Almost every paper in the top 9 that I have shortlisted in the top 30 is Google. Number 9 is Spanner. It's a difficult paper to read. Frankly, distributed consensus is difficult as a subject, in my opinion. I've read a lot of stuff around this papers. Leslie Lamport has a website which talks a lot about consensus, but even then, it doesn't seem very easy to understand. Okay, so as a software engineer, don't beat yourself up too much for not understanding everything, but if you go through it once, you'll get a general idea of how things are working. Number 8 is Dremel. This is considered one of the best papers I think ever written. It's by Google, as you can expect. It talks about very large scale data sets. How do you run interactive analytics on them? So interactive analytics is like you're an operations team person or a product team person, and you come and you want to fire a query. So it would be like Google Analytics, where you have some data and then you want to filter some column out, or you want to aggregate something, and you have to do this in real time. So Dremel allows it. Now Dremel has inspired many papers. It is an inspiration for Apache Impala, and if you have checked out Google's BigQuery service, it runs on top of Dremel. This paper has been featured in VLDB, definitely worth a read. Number 7 is, I think, the world's most popular software engineering paper, for sure, which is Google File System. You have probably read it. If you haven't, then you've definitely heard of it. And if you haven't heard of it, then please go check it out. It's really nice. The reason I'm putting it at number 7 is probably because, you have already gone through it. I would say that a lot of the ideas in this were so awesome at the time that it came out that it's definitely worth a read. Many of the ideas have been ingrained into software engineering now. Like if you have joined software engineering after 2015, then you probably have heard of many of the concepts that this talks about. But still, it's worth a read. It's worth just going through them again. This is pre-NoSQL hype, pre-machine learning hype, pre-MapReduce hype. This is the thing where everything started. So do have a look. Number 6 is BigTable. Again, another paper from Google. I said that, there's just 2 non-Google papers in the top 9. We have reached 6 and gone through Google for a long time. BigTable though, which is number 6, is something which is written on top of Google File System. It's a NoSQL data store for Google. If you are storing especially web pages, then it's super optimized. If you have Google's crawler, searches the entire web, picks up pages from different places, stores it for processing later. Those pages have versions. So how do you store that efficiently? These are some of the problems that BigTable had to face. It's a very early paper by Google, but still worth a read. Number 5, we are in the top 5. And finally, a non-Google paper comes in, which is from Meta, and it's Hive, which is a warehousing solution by Facebook. It's very interesting. I think it's now been open sourced. The idea is that you want to store a lot of data, and then you want to scan through that data efficiently. Hive is an old paper. It's on data storage. It's an old paper. Again, many of the principles might already be well known to you, but it's worth looking into. If you're a data engineer or a software engineer, it's amazing. Number 4 is Pregel. Pregel is a graph processing system by Google. It processes graphs in batches. Very interesting to read, because when you're looking at PageRank algorithms, or you're looking at any kind of graph processing which is done at Google scale, it could be even social networks. If you're thinking about emails, who's connected to whom, whether you should mark something as spam, all of that graph processing can be done by Pregel. I don't think Pregel exists in Google anymore, but the algorithms and the ideas are really, really interesting. Definitely worth a look. Number 3 is the last non-Google paper which you'll see in this list of 30, which is Facebook Tau, which stands for the Associations and Objects. It's a graph processing in-memory meta system. It's written on top of Facebook Memcache. One of the problems with Memcache being used by Facebook engineers for social networks was that their engineers had to learn a lot about Memcache. So they extracted that logic, they put a wrapper around it. But Tau is not just a wrapper. It's like a really, really interesting, complex, practical wrapper. So worth looking into. You can think of this as a graph database which is powered Facebook scale. The last 2 papers are both Google. They're a little less heard of. The reason I put them on top is because they're very easy to read, very interesting. They pick a topic which is slightly different. Software engineering, but slightly different. So number 2 is moving beyond end-to-end path information to optimize CDN performance. It's a really long name, but if you read the name carefully, what it talks about is how do you get data efficiently from a CDN. And usually we think that if you have connected to a CDN quickly, then you'll get data quickly. But the fact is, a CDN is also just like a server. Once you connect to it, you might have to wait in queue for a while. And also, connecting to it doesn't just mean the physical distance has to be low. You might have a really long path around a CDN. So how do you avoid that? Even though you're able to send the message in a really straightforward fashion, you might be getting back the message in a long roundabout path. Google did some analytics around this and discovered that this is actually a serious problem. We can talk about efficient cache algorithms, we can talk about efficient connections, but the fact is, if the path is not optimized, or if the queue size is too small for a CDN, then you'll face serious issues. Worth a read if you're a network engineer, and definitely worth a read if you're a software engineer. The final paper is by Google. It's probably the hardest paper I've read. I had to check out their video, read some other blogs, but when you understand it, it's like, wow. It's on load balancing. The algorithm is called Backend subsetting. This is used by Google's autopilot system. Autopilot is the load balancer, which gets requests and then forwards it to the right place for Google. It's a difficult algorithm, like I said. If you know about consistent hashing, if you know about round robin, if you know about random assignment, then it's good to start with. If you don't know about it, then you can check out the link in the description for consistent hashing. But the main idea is that at Google scale, request routing is super important. Optimizing on their load balancing algorithms can save them millions of dollars. So they do a lot of research around this and they find the best possible algorithm, which is a trade-off on complexity, which is a trade-off on what happens if things go wrong. So fault tolerance, when things are going fine, then what's the latency like? So there's a lot of things that they consider here in this paper, backend subsetting. Then they come up with an algorithm which is difficult to understand, like I said, but worth it when you do understand. Thank you so much for watching this video. We talked about 30 papers which are worth your time. Most of them, to be frank with you, are from Google. A large section of the remaining papers are from Meta. That's what I saw after going through about 100 so papers on software engineering. If you have been paying close attention, then a lot of them have been on data analytics and data storage. A reason for that is because recently there's a lot of focus on data analytics and data storage. That's probably one step away from machine learning, which is coming out recently. Right now, we are talking about the nascent stage of machine learning, which is anomaly detection. I've seen Microsoft, Facebook, Google talk a lot about anomaly detection now. I think that's the most practical place to put machine learning in software engineering to start with. All the best though. I hope you read all of them and I hope that they really add a lot of value to you. I think that as software engineers, it's really worth your time. Let me know which is your favorite paper, and if you have any suggestions on adding papers to this list, do let me know. I'll do that in the description. See you. Bye-bye.